Now what we're going to look at is we're going to take those ideas of electron configurations and look at them more for orbital diagrams. We've already done a little bit of this, but this is to go over all the rules for it, make sure we're comfortable with them. So what we have shown here, sorry about that, is a pictorial representation of the hydrogen atom. The hydrogen atom has a single electron where n equals 1 and L equals 0. That means it would be a 1s electron. We also know m sub L equals 0 because it has to, and m sub s in this case will be plus 1/2, although it could be plus or minus 1/2. What we do is we draw a box like shown here. So we have a box, we label it for the orbital that it represents, and then we have a half arrow, in this case going up because of the plus 1/2. I will note, when you look at a lot of examples, basically every chemist I've ever met starts with up arrows for plus 1/2. There is no reason to do that necessarily. It is not that up arrow always comes before down arrow. Just so you know, because I think as a student it can feel weird, like it feels like, oh, there's some hidden rule, it has to be plus 1/2 first. No, it can be minus 1/2 first as well. It's just we tend to do that just as sort of a custom because we tend to write the up arrow on the left and the down arrow on the right. So this is just how we show it. So now, these are some additional atoms. So we have helium. Helium is still limited to the 1s orbital. Both of the electrons are at n equals 1, L equals 0, m sub L equals 0, but m sub s now equals plus and minus 1/2. Starting with lithium, remember the way that numbering went, right? We're in the 2s block as you're going across the periodic table. Or if you're filling it by the off-ball principle in terms of using that line diagram that I showed, 2s comes after 1s. So the third electron has to go into the 2s orbital because s can only fit 2 electrons in one s orbital. So 2s is the next orbital. And then beryllium is 2s2, so it goes up arrow, down arrow with that. Now once you move past that to boron, boron has 5 electrons. It is the first electron that first atom that shows up in the p block. So it goes into the 2p orbital for its first electron. Now, for carbon is the first time we come up with a new rule called the Hund's rule. It hasn't come up yet because it hasn't been an option. Hund's rule is that for the lowest energy configuration of an atom, you expect the electrons, if they're in what are called degenerate orbitals, and all degenerate orbitals means is that they are the same energy, you want to have the maximum number of unpaired electrons. So because the 2p orbital has 3 possible values for m sub L, -1, 0, and +1, there are 3 boxes. So within those 3 boxes, you're going to end up with 2 unpaired electrons. And they'll usually be pointing the same direction. So either both up or both down. So we put them in separate orbitals before we start putting them together, as this is a lower energy configuration. You can then keep going through, and here's some more examples of nitrogen has its adds a 7th electron, I can do math, 5th electron in the n equals 2 level. So it has 3 unpaired electrons. And once you get to oxygen at 8, this is the first time we've had to pair some together in the p orbital because we've run out of empty p orbitals. Then fluorine has a second paired one, and then finally neon has 3 paired ones where all the 2p orbitals are completely filled. Now, we want to talk some about these particular electrons and which ones we care about most for the purposes of our chemistry class. All electrons are there, but certain ones participate a lot more in chemical reactions. So the electrons occupying the orbitals in the outermost shell, the highest value of n, are called valence electrons. Then you have electrons occupying inner shells, so things below that top n, that are called core electrons. So usually the valence electrons are going to participate in a lot more chemistry, so the number of valence electrons determines the chemical behavior of many of our atoms. They're one of the driving forces, whereas core electrons tend not to interact a whole lot in chemical reactions. Note that when you fill up all the valence electrons into a particular shell and it is completely filled, that ends up arriving at the end of the periodic table on the far right, and those atoms at the far right are called a noble gas. And because of that, we give their electron configurations the special name, noble gas electron configurations. The reason we say that is because those configurations are especially stable. Noble gases incredibly rarely react. At one point, the chemists thought they would never react. With enough effort, chemists have been able to get them to react with fluorine primarily, which is our most reactive atom on our periodic table. But in general, noble gases are incredibly stable. They have electron configurations that are really good at being low energy. And so most atoms start to go towards a noble gas configuration, either gaining or losing electrons, whichever is simpler. And because of this, we'll also use these configurations to help with our representations of atoms that have large numbers of electrons. We don't have to write out like 62 electrons for an atom. So how do we do that? This example here is for sodium. Sodium has a total of 11 electrons. The first 10 are core electrons, the 1s2, 2s2, and 2p6. The last electron, 3s1, is in the highest energy level and is called a valence electron. For this reason, we can abbreviate all the core electrons together to match up with the noble gas that has that configuration. So neon is 1s2, 2s2, 2p6. So what we'll do for sodium is we'll just write it as neon plus a 3s1. And that makes it easier to write. It also focuses on the electrons that are most reactive and the ones we're most concerned about. I am not as concerned about the 1s electron in sodium. It is very unlikely that it's going to do very much chemistry. On the other hand, this 3s1 electron is very active and ready to react with lots of different types of atoms, and so it's the one I'm most concerned about. It is the lowest energy electron, so it is the easiest to lose for sodium, and so can participate in a chemical reaction where it might leave the sodium atom. So here are some examples of how we can abbreviate those, just to show you some different ones. So for example, lithium is the first atom. So I think with all of these, it's good to look at a periodic table at the same time. So if you look at a periodic table, you'll notice lithium occurs, it's atom 3, and it is the first one in group 1. So the noble gas before it was helium. So you get helium 2s1. This is the same thing as saying 1s2, 2s1. With the helium abbreviation, you don't save a lot of time, but as you go further, you really do. So for example, for potassium, I'm going to write this out the whole way. You'll see why we like to have abbreviations. So it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. So you can see this starts to get kind of unwieldy. I do want you to know how to write the complete configuration because we want to make sure you understand what that abbreviation stands for. But in most instances, you will use this noble gas abbreviation as a way to write your electron configuration for atoms. Below that, group 2 is shown, and similarly, each of those atoms has a second electron that it has gained past the noble gas configuration, so it shows up as s2, with beryllium being 2s2, magnesium 3s2, calcium 4s2, with the noble gas written before it. Here, this is easier to check out by PowerPoint. You could also see it if you're looking at this from somewhere other than my class. OpenStax has this in their textbook. You can see a slightly bigger version of this, but it shows that these atoms all tend to sort in terms of when you go to the columns based on the number of valence electrons. So everything in the first column is S1. Everything in column 2 is S2. What this means is those atoms tend to have somewhat similar chemical properties. In particular, they tend to react with similar atoms. So sodium and lithium are both likely to react with, for example, chlorine. So because of this, it's easy to predict properties of other atoms compared to the one you're looking at if they are in the same column. Note that this also, if you look at this really carefully, it shows that some of the configurations don't go in the exact order that we've told you in terms of when you look at that chart. There are some properties that cause a few of them to change a little bit. For the purposes of the class I teach, I'm not worried about you dealing with those. You don't have to memorize all of the exceptions. You can know that they exist, and if I were to mention them, it should be okay. It shouldn't bother you, but you don't have to memorize, for example, that chromium is actually 4s1 3d5 rather than 4s2 3d4. And it has to do with some things about particular stable setups when shells are half filled in addition to completely filled. And so that leads to some of these exceptions. Don't stress about them for my course other than to know they exist. And if I give you an electron configuration for an atom using that, you should want to identify what atom it is. So we're going to do some practice here, and I'm going to show some problems, and then we'll go and show back on there what they are. So we should be able to go both ways. So for example, let's say I asked, what is the electron configuration of sulfur? So sulfur, if you look at a periodic table, is in the 16th column. It's 2 away from the noble gases. That column is also sometimes labeled 6A, depending on what the periodic table you have. Some periodic tables are divided into A and B, and some just use 1 through 18, and some use both. So sulfur, the first thing I do is I go and I look for the closest noble gas to the left of this atom. So sulfur is at 16. The first noble gas before that is neon at 10. So this is neon. And since neon has 10 electrons and sulfur has 16, I should expect that I need 6 more electrons to show up in my valence to have enough. So counting that number helps to identify atoms. So for example, I know that neon stops at 2p. So if I was using the version where I write out like 1s, 2s, 2p, 3s, 3p, 3d, neon has got 1s filled, 2s filled, and 2p. So what that means, since 2p is filled, my next electrons go into 3s. And s only can fill 2 electrons, so it's going to be 3s2. And then I have to go to the next one. After 3s, we go to 3p. So 3p can hold up to 6 electrons. All s orbitals hold 2, all p orbitals hold 6, all d orbitals can hold 10, all f orbitals can hold 14. 2 per little dash for how many orbitals they have. So since it can hold 6, but I only have 4 more left. Remember, sulfur had 6 more than neon. 3s2 contains 2 of those, so I have 4 left. So this would be 3p4. And this would be my electron configuration. You could also do it by going past neon and noticing you cross through 2 atoms in the s block in row 3 and 4 atoms in the p block in row 3. So 3s2, 3p4 is what you would do after neon. Both of those answers would be acceptable. In addition, if you wanted to draw an orbital diagram of just the valence electrons, you could have a box labeled 3s, and then a set of 3 boxes that are close together labeled 3p. And they would be symmetric if they weren't hand-drawn. So 3s has 2, and then 3p has 4. And remember, you put them unpaired first, and then you start pairing them. And we generally pair from left to right. It is not that that is inherently better, but that'll match up with what you'll tend to see. There's not some special rule that says it must be the left box before the middle box, though. Just to mention, because I think a lot of times, because we do things a certain way, students might assume, oh, there's some rule for that, but there's not. Okay, so that's how you would do that configuration. Now, we can also, and we can go over here and we can see, oh, look, sulfur shows up right there as 3s2, 3p4. That matches up with what I came up with as well. So I want to do another example. Now, let's clear all this off and go back to my pointer. So let's do this the other direction. Let's say I told you what atom has this electron configuration. I'm not going to write out the word this electron configuration. You can do that if you'd like. What atom has this? And I'll just point to electron configuration, so I don't have to write it again. So what atom has this? Let's say we had, I'm going to say argon, 4s2, let's say 3d3. So what we can do, and I think this is the easiest. Technically, you can go to how many electrons are there, like go through the s block and d block. But a really easy thing to go is go, oh, argon is at 18. So this has 5 more than argon, and I'm told it's an atom. You have to be told it's an atom. So assuming it's an atom, you are 5 past 18. That's 23. So 23 gets you to vanadium. So this is V. This helps especially when you get to exceptions. For example, if I'd instead asked what atom is argon, 4s1, 3d5. Note, I don't expect you to memorize this exception, but I expect you to be able to deal with it and identify what the atom was. So this is 6 past argon. And 6 past argon will get you 1, 2, 3, 4, 5, 6 to chromium. On the other hand, I've had students that will just go to the 5th atom in the D block, which would be manganese. So this is a way to make this easier to identify. It makes it so exceptions aren't as big a deal. They're easier to work with when you deal with it this way. So you should be able to identify both what is the electron configuration of an atom, and then also what is the, if I have a configuration, what atom is it? Finally, let me do one D block one to help remind you of one of the rules that we have not had to use a lot about how the N values change. So let's do one more like that. Let's do the electron configuration for zirconium. So zirconium is atom 40. It is after krypton. So we write krypton. And then it is 4 after krypton. So krypton ends at 4p. The next one after 4p is 5s. So we have 5s2. We then have 2 more atoms, so we're going to say that we go to 4d2. Note that it went down to 4 because you're in the D block. The D block shifts down 1, while the F block shifts down 2 when you get to it. As a reminder, if you're following along the periodic table, if you just memorize where you draw the lines through things, like I did in my previous video, then that's already there, that after 5s you'll get to 4d. So either way, that would be my answer. It would not be 5p2. It doesn't fill the p orbital until after the d orbital is completely filled. Just to go with that, for example, if you had 10, that is all the way at 50. You have krypton, 5s2, 4d10, and then 5p2. Note, depending on what resource you're looking at, you might see it listed as krypton, 4d10, 5s2, 5p2. Both of these would be acceptable in my book. They both show the same idea. It just has to do with how they tend to write them. You'll see them in different ways. So do know that. Okay, so that's something you should be able to do. Make sure you do electron configurations both ways. They're very common questions for professors to ask, whether they're me or someone else's. They're just good things to see. Hey, do they know how to move around this thing and do this? Now, everything I just did was for atoms. But in the previous chapter, we've talked about the concept of ions. Remember that ions form when atoms gain or lose electrons. So a cation forms. It's a positively charged ion. As a reminder, it's cat. It's got a plus sign in it, T, if that helps you remember. So the positive one is a cation. It loses electrons. They're removed. So for the main group elements, the electrons were added last, are first removed. For the transition metals and the intertransition metals, they lose their s electrons first before they lose their d or f. It has to do with the fact that the energy levels for those orbitals are very close, and as the atom gains electrons, it's going to shift them a little bit, so it changes which ones are likely to leave. So, and then if you have an anion, it goes the other way. It gains electrons, and so you'll put new ones in. So let's look at a couple of examples. Let me see if I've got one already written. I do. Who would have thought? So let's start with sodium plus. The best way I find to do these is to write the atom first and then come up with the ion. So sodium, Na, is going to be neon, and then it's going to be 3s1. Almost messed that one up, wasn't thinking. Now, this is for sodium. For sodium plus, it's lost 1 electron, so it's just going to be neon. It takes that electron configuration. You could also maybe see it written as helium, 2s2, 2p6, now that those electrons are valence, but I think this first area is more likely what you'll see more often. Now, let's do one more for this. Let's do phosphorus, and then I want you to try a few. So phosphorus, in its atomic form, is going to be neon, 3s2, 3p3. So if it forms a 3- ion, it's going to gain 3. That will be neon, 3s2, 3p6. And even less likely, but you will see sometimes, you could also see it written as it has become argon. Would also work. I'd be fine with either. So what I suggest now is that you pause for a second and try the next two. Okay, let's go over those now. So we can start with aluminum. Aluminum plus 2. So Al is neon. Let's make sure I got this right. Yep, 3s2, 3p1. Now it's formed a 2+ ion, so it's going to lose 2 electrons. It'll lose the p1 first, and then one of the s's. So it'll be neon 3s1. Note that it is not always going to take a noble gas configuration. So it is possible to have ions that don't just go to a noble gas. This is a good example of that. Second, we have iron, 2+. So we'll start with iron itself. So iron is argon, 4s2, and then 1, 2, 3, 4, 5, 6d electrons. So 3d6. If you were to form a +2, you would remove the s electrons first. That's what happens with our transition metals. And so you would have simply 3d6. This is the one that looks a little different, but that'll happen for all your transition metals. It will lose the s electrons first before losing d or f electrons. So you should be comfortable with writing electron configurations for ions as well. In addition, if we were to give a question like, oh, let's say, what +1 ion has this configuration. So I'll just say config. So let's say I told you it was just argon. But it's a +1 ion, not an atom. So what you can do is you can see argon has 18 electrons. Since it's a +1 charge, that means the original atom must have had 19 electrons. And an atom with 19 electrons has 19 protons. So the atom with 19 protons is K, potassium. So this would be K+. So for anything where you have to go this direction, we would have to tell you what the charge on the ion was, but you would be able to figure out what the original atom was by adding or subtracting electrons from that number that you have to get what it originally had. For a positive charge, it must have originally had more electrons. For a negative charge, it must have had fewer electrons. So figure out how many electrons it had when neutral. The number of protons will be the same, and that's how you can find the symbol for the atom. And then just match the charge to what it is. So this was +1, so it'd be K+. If it had been something like calcium 2+, you'd write a 2+ after. Okay, that's a good place to stop there. In the next video, I will be working through materials on properties of atoms based on their position on the periodic table. But this ends it for electron configurations.